Hello, this is lecture N+1 of Emergent States of Matter, February the 24th, 2021. And we're going to continue our discussion from last time of the persistent currents in a superfluid. So just to recap, what we discussed last time was the idea that if I write out the if I write out the idea that we have a condensate, in other words, a macroscopic occupation of a single quantum state, which we'll call phi, which in principle is spatially dependent, and then what we saw was that the current in that state is just given by the gradient of the phase of the wave function. In other words, that you have a potential flow, that's what it's called, when the velocity of the current is proportional to the gradient of some other function. And what that means then is that because it's the gradient, that implies automatically that the curl of the velocity field is going to be equal to 0. And so that's exactly the condition that we required for superfluidity. In other words, the condition that we get no drag. So what we started doing then in the last time was we wanted to start to explore the role of topology in the system. And the way we were going to explore that was by looking at superflow in an annulus, as shown down here on the bottom left. And the idea was we were going to look at what happens to the wave function as we track our way around the rim of the wave function of the annulus. So let me just draw the annulus over here, and then so here are these points R1, R2, and R3 on the left, and on the right here I've sketched for you what the wave function might look like in the Argand diagram at those different points, and you can see that the phase is varying. Now, the key point is that as we go round the loop, as we go round the annulus along the curve C, when we get back to where we started, the wave function has to be single value. That's a fundamental tenet of quantum mechanics. And so what that means is then that the phase must have changed by a multiple of 2 pi. So what we know is that any expectation value will be should be the same. So what that means is that the phase can vary by a factor of 2 pi, and so we must have a multiplier of 2 pi as we go round the loop. So let's just see what that actually means. And what I told you at the end of last time was that implies that the velocity is quantized. And so let me just explain why that's the case. So let's suppose that our annulus has a radius r and the thickness of the annulus, let's call that little l. We'll see that that thickness is very much less than the radius. So essentially then what we can say is that if I want to compute the line integral of the velocity around this loop, so I'm going to go around this curve C, I'm going to compute the velocity, the superfluid velocity, as a line integral. So we're going to assume that we have over here a superfluid velocity Vs that is being driven by the gradient in phase. So this integral is then, this Vs dot ds is just h bar over m times the line integral of the, that's interesting, the line integral of the gradient of the phase dotted dr. I don't really know why I've got this funny square here, so maybe that's some super slick Apple feature. Well, there we go. So so that's putting in our velocity as a gradient in here, and then of course all this does, the integral round around this curve. Well, this is what we know is that grad gamma dot dr is by definition just d gamma, right? Because that just says that d gamma is equal to d gamma by dx plus d gamma by dy, etc., plus d gamma by dz. So that's just grad gamma dot dr, and grad gamma dot dr is just d gamma. And so what we have then is that the line integral or around this curve of Vs dot dr is then equal to h bar over m times the change as I go round here of the phase d gamma. And what we're saying is that this is a multiple of 2 pi. So what we require is that the wave function, which we call phi, must satisfy the condition that the phi at the start of the circuit is equal to phi at the end of the circuit as I go round the curve C. But that means that gamma at the start does not have to equal gamma at the end. And in fact, all that we require is that gamma at the start is equal to gamma at the end plus some multiplier, some 2n pi, where n can be 0, plus or minus 1, plus or minus 2, and so on and so forth. And so then what that tells us is that the line integral around this curve of Vs dotted dr must then equal h bar over m times 2 pi n. And what is this this integral of Vs dot dr? Well, this we can just simply write as Vs times 2 pi r, where r is the radius over here. And so what we have then, that this is equal to h bar over m times 2 pi times n. And so you can see that the velocity is just h bar over m 2 pi r, like so, times 2 pi n, like so. And so that tells us then that the velocity of the superfluid is actually quantized. And so that's a remarkable fact. And we'll talk. Well, let me just say then what this means for the persistence of the superfluid state. So what does this mean?
So can I ask a quick question?
Yes, you can.
Are we assuming that we are starting steady state so that the V is constant throughout the curve? Or...
Yes. I've not talked about. Or remember, we've not talked about the time dependence here of how we established it. So what would happen is if I started off with some spatially varying wave function, it would very quickly settle into this kind of into some kind of a uniform state, and how it relaxes to that. One can model using things like the time-dependent Ginsburg-Landau equation and things like that. So here we're really just interested in steady states where the velocity field is spatially uniform. So let's ask what this means for the persistence of the state. And so my claim is the following. What we did was we considered that this was a BEC, or if you like, off-diagonal long-range order, into a particular wave function. So usually we think of this as being just the k equals 0 mode, which is just the usual zero momentum state of a condensate. But if I go into other wave functions, other states, phi, they give you some steady state current, as we've just seen. And if they don't have k equals 0, then what these other states would have, if I were to compute the phase, well, that's going to have higher energy. So, for example, in this particular state over here, if we just have a uniform state with n equals 0, that just means the fluid is at rest. The lowest state is with n equals 1, and so the fluid is going around at the lowest quantization. The more we increase n, so the more we increase n, the faster gamma rotates as we go round the curve C. And when I say faster, what I mean is if I go round the curve once in space and gamma changes by 2 pi, that's the slowest it can change. But I can also go round the curve in space once, that's 2 pi in real space, but I can go round twice in the order parameter phase, and so that's twice as fast. I can go around 6 times, 6 pi, so I can go around 3 times, and so on. So as we increase n, faster gamma rotates as we go around C. So by that I really mean is that gamma rotates n times, rotates by 2 pi n times as we go once around the curve C in space. And so what is the implication of that? Well, the implication of that is that if I were to compute the gradient of the wave function, so this gradient, or really grad phi squared, is then going to be increasing with n. And so what that means is, because it's increasing, that means that I've got more gradient terms. So then I compute the actual energy. That means that these states will have higher energy. So the greater the number of the greater the gradient of the wave function, the more nodes there are, the higher is the energy. So these different states correspond to different energies. So what we've just learned from this argument, i.e., the higher n states have higher energies, and these must then be metastable current carrying states. Now, why do I say metastable? Well, what I mean by metastable means a local minimum, not a global minimum. So what that means is that the kinetic energy of the superflow is locally minimum at the quantized values that we've just calculated. And so if I were to compute the energy as a function of n, so what you would get is something that looks like this. I'm only going to draw this schematically. So the energy is basically going to go like v squared, right? It's kinetic energy. But now we've got these local minima at n equals 0, 1, 2, 3, and so on, -1. So this thing kind of looks something like this, and the same thing over on the other side. And so what you can see is that there are these energy barriers between the states. So there's energy barriers between these states, these current carrying states, and so therefore they're metastable, they're local minima. But if you excited them enough, then you could go from, say, n equals 2 to n equals 1. But we know that in order to do that, you'd have to literally make a global change to the system. So to get over an energy barrier would require escaping over an energy barrier between two macroscopic states would require the energy that will scale with the system size, because this is a macroscopic wave function, so it will depend on the number of particles in the superfluid state. And so basically it's just like removing a topological defect. So the current is in some ways like a topological defect. And it has a winding number. And so that means it's topologically stable, just like a topological defect is. You can't change it by any local change. And so because of this stability, we say that these currents are persistent currents. They will last forever. They're very long-lived, unless a huge thermal fluctuation comes along. To change the topology. So that's what we have in persistent currents, and this is perhaps the most direct evidence of superfluidity. So just a little bit of terminology here.
Could I ask a quick question?
Let me just finish what I'm writing on this. So the terminology. So when we talk about this line integral of the superfluid velocity around this curve. So this is just like computing a topological invariant. It's like computing the Burgers vector around a dislocation. And this thing has a name, it's known as the circulation. So the correct statement is that in a superfluid, in a non-simply connected domain, the circulation is quantized. And I say circulation rather than velocity, because the velocity itself depends on the geometry. So you can see here, for example, that the radius of the system is in there, but the circulation is quantized in just units of 2 pi and fundamental constants. So it is a more useful statement to say that it is circulation that is quantized. Okay, so Dimitri had a question.
Yeah, how do we interpret the non-integer n states in the graph that you drew?
Yeah, so those states, those would be states that are not spatially uniform states. So instead of having the velocity be a constant all the way around, maybe you would have some, well, what you would actually have was some kind of defect configuration in the state. So it would be a non-uniform configuration of the order parameter, and it might not be a steady state. So,
I see.
so for example, if you were say over here, say at this point between these two energy barriers, so what you probably know is that usually corresponds to a configuration that is a non-spatially uniform configuration of a field between two minima. It's called an instanton, and it's like a sort of critical nucleation. A critical nucleation droplet in the system. So it's a kind of non-stable state, a non-spatially uniform state of the system.
I see. Thank you.
Okay. Is there still a gamma defined for such states?
Yes, but it won't. But it won't. But the gamma that we've defined is one that basically, if you have a constant velocity, then so let's just say that. So let me just write down, because these are good questions. So so in between the metastable minima, are these spatially non-uniform unstable field configurations. And then these are basically in material science, you might call them critical nucleation droplets. In the non-equilibrium statistical mechanics, you might call them instantons. In quantum field theory, you might call them instantons. So they're spatially non-uniform, unstable field configurations. And then the question that somebody asked, I think maybe it was Daniel, is that if the velocity is a constant, which is sort of what we've been assuming when we write down this quantization here. So the velocity is a constant. That means that this constant is proportional to grad gamma, and so it means that gamma is increasing linearly as I go around my curve. And so if I'm having these non-constant V's, they would correspond to spatially dependent gammas.
Yeah, so what I was wondering is then, are those gammas still single valued?
The wave function has to be single valued.
Oh, sorry, yeah, single valued mod 2 pi.
Yeah.
Like, it seems I'm confused then how we can have, if velocity is still grad gamma for some nonlinear function gamma, I'm still confused about how we can have states in between 2n. But I don't know if there's a...
They're not steady states.
Okay.
So when
but instantaneously there's a gamma, right?
These are steady states. Okay, that's what we assumed. So they're steady states, and we also, in writing this down, we assume that they are spatially uniform, meaning the velocity is constant. Whereas I can make any field configuration I like as long as it's single valued. And it'll be just some configuration which will then evolve in time and decay or do something according to the Schrödinger equation.
Okay.
Okay, so let's move on. So let's just talk about, I want to just finish this section by talking about the role of topology. So it was very critical in this discussion that we had an annulus. And not something, not a simply connected domain. So let's just quickly see why that is. So, so let's suppose that I have a region of fluid. So here's my fluid. It is, and now let's suppose I draw my curve through this. So here is my curve, curly C. Well, then if I draw this curve like so, then I can draw a surface that spans this. So I'm not really doing a very good job of drawing the surface. So let's just call this a surface S, a spanning surface, which is bounded by the curve C. And then what I know is that in this region here, if I compute the circulation, so now I go round like this, so that I can use Stokes' theorem, and so that then is curl V dotted with ds. So when I say ds, what I mean is a little thing sticking out like that. And then we know, because this is a superfluid, so curl V is equal to 0, and so this is equal to 0. And so what we've learned then is that the circulation must be 0 by Stokes' theorem. And so the only way out of it is have a non-simply connected domain. And so how could we have a non-simply connected domain? Well, there's two main ways that we can do that. So one way to do that is to have an annulus. So in other words, in the middle of in the center, there is no superfluid. So that's one way, and the other way is to have a region where the wave function is equal to 0. In other words, a topological defect. So the picture that I have to have then is my region has to have in it. So here's my region, and then somewhere in the middle of this, there has to be at least some region where the wave function is equal to 0, either because of the topological defect or because I have an annulus. And once I have this, then of course it's possible for me to have a non-zero circulation. So that's the idea. And so now I want to talk now probably for the rest of the lecture about these topological defects. So let's talk about them. First of all, historical note. So the idea of quantum vortices was suggested by Feynman and Onsager in the 1940s. Or maybe it was the 50s, I've forgotten. And you know, as you know from homework sheet 1, because we have a complex order parameter here, which comes from off-diagonal long-range order, then we can have topological defects in d equals 2 and d equals 3. So if we have a superfluid film, we can have a pointwise topological defect. If we have so this can be a film of superfluid. Which will have a point defect. If we have d equals 3, so we have bulk superfluid, we have a line defect. So we can have these defects. Now, what Feynman and Onsager were trying to understand was actually an experiment, and the experiment was really quite interesting. So the idea came from experiment, and this is Osborne's rotating bucket experiment. So what is it? What is the basic idea? Is this? Let's suppose I have a perfectly inviscid fluid where curl V is equal to 0. Then what you would expect is I take a bucket and then just start to rotate it. The fluid, there's no friction. The fluid will not be rotating with the walls of the bucket. So there's no mechanism to create a rotating flow. So let's just say that. So in a perfectly inviscid fluid, which means it has no viscosity. So we've got curl V is equal to 0, just like we've seen before. There's no mechanism to create a rotating flow. So what that means is that if I put such a fluid in a bucket and rotate it, you would expect that it would not rotate. So in a bucket that is rotating, is the superfluid also rotating. So that's the question, and we can now try to answer this question from our knowledge of superfluid helium. So let's think about what we would expect to see. So let's suppose I have helium-2 in a rotating bucket. So we know what this thing is equal to. It's equal to a superfluid component plus the normal component. Okay, so I'll write it down like that. And so what you would expect then is that the normal component has viscosity, and so this will rotate. But the superfluid component does not have viscosity, and so this will not rotate. That's what you would expect. So how would we know if it's rotating? Well, we'll know if it's rotating by looking at the meniscus. So let's suppose I've got my bucket. So let's draw a bucket like so. So here is an axis of rotation. So I'm going around like that. This is the radial direction, and then what we know would happen in a regular fluid is that you would have a meniscus which would be shaped like that. So this is the fluid under here, and this meniscus has a shape, and the shape is that the height of the meniscus as a function of r is just going to be a parabola. And you've got gravity going down like that. So that's basically just really working out how to balance the rotational energy against the potential energy. And so what you get is the meniscus shape for a rotating fluid has this form like so. And so what would happen in superfluid helium? So in helium 2, this won't happen quite like this, because only the normal component is rotating and not the superfluid component. So what you'd expect, so this is for a regular fluid. So in helium 2, what you would expect is only a fraction of the fluid is rotating. And what fraction would that be? Well, that fraction is going to be the fraction, which is the normal component, rho n, over the total density of the fluid. So this fraction would be this. And so what that means then is that we would expect that Z of R, the shape of the meniscus, would be the rho n at whatever temperature you're at below the lambda line, times omega squared R squared over 2g. So this is what you think you should get. And the strange thing is that it's not what you get at all. What you actually get is this. Okay. So actually, let's call this equation star, and this equation triangle. So actually, what you see, equation star, not equation triangle. And so that's a remarkable thing. So what that says is that the meniscus is not temperature dependent. And so it seems that the entire fluid is undergoing solid body rotation. So this was a big surprise, and so so what that then says is, well, if that's true, then what it says is this: if I have a uniformly rotating fluid, or a uniformly rotating body, then the velocity field at the point r in it from the axis is given by the cross product of the rotation, the angular velocity cross r. So that's what the fluid is actually doing when you're rotating the bucket. And why is this surprising? Well, if I take the curl of this expression, so I take the curl of V, then you just use the formula for curl, and you can work it out. And so what you get is you get 2 omega, which of course is not 0. And so this seems to be, that this whole thing seems to be an apparent violation of the superfluid condition. So what actually happens then? Well, so this is where it gets interesting. So what Onsager and Feynman guessed, and this was confirmed about 10 years later, but by visualization, is that you generate a bunch of quantum vortex lines, and the vortex lines are threading throughout the bucket. So let's draw a picture of the bucket over here. So here's our bucket. Here is our meniscus shape. And the whole thing is doing this this solid body rotation about this axis, like so. And now what is happening is that you're getting these quantum vortex lines that are, I'm going to sort of sketch them like this. And actually, they get closer together near the center. And these quantum vortex lines, as I'm going to show you, self-organize, and actually they form a more or less a crystalline array. So these vortices, as we call them, self-organize. Because they interact. And we'll work out how they interact in a few minutes. A hexagonal array in the center of the bucket. And as you go further and further out from the center, it becomes somewhat non-uniform because of the meniscus shape. So that's the answer of what happens. So if we were to look down on this thing from above, what would we see? So if we look down on it from above, what you would see is a vortex core like so, and then around the outside, around outside, you would have a superfluid flow like so. And this thing over here is the vortex core. So that's what you see, and to a good approximation, the flow around each vortex line is cylindrically symmetrical. So if I were to ask what happens around it, well, I already know the answer to that. So if I go around each vortex line, well, what I know is that if I take the line integral of Vs dot dr, so that is quantized, that is equal to n times Planck's constant over m, like so, and so what I find then is that 2 pi r times the magnitude of the superfluid velocity as a function of r is then equal to nh over m, and so what I learn is that that away from a quantum vortex line, the superfluid velocity as a function of r goes like nh over m times 1 over 2 pi r. So we have then a velocity field that decays as 1 over r as you go away from a vortex core.
Sorry,
So,
answer question.
you want to okay, and then you can, yes. So what is the core of the vortex? So the core of the vortex is about 1 angstrom in size, and it's roughly like like some kind of line of missing atoms. I don't really know. I don't really like to say what it is atomistically, because we're talking about concepts here which are sort of macroscopic. So that's what people like to say. It's hard to really be sure what's really going on there, but that effectively is what's going on inside the core. And in the core of the vortex, there is vorticity, there is circulation, because it is normal. And it's normal because it's a topological defect. And so there's no off diagonal long range order there. Okay, so I'll take Quansen's question if it's a quick one.
Okay, so does that formula for the velocity field as a function of r only valid close enough to the core? Because I guess there are a lot of vortices.
Yes, yes. So I'm going to get to that. So just be patient.
Okay.
Yes, so perfectly good question. So that's around each vortex line in isolation. For example, let's suppose I very slowly rotate a bucket. Then I just get 1 vortex line right at the center. I just keep it at a very slow speed. That will be roughly speaking, that would correspond to this velocity profile. Okay. So the next question. So can you mute your microphone, please, Quansen? For some reason, I think because the headset you wear, I think, well, whatever it is, on the microphone, it has a kind of weird feedback. So, okay. So the next question that we want to ask then is that's one quantum vortex line, but we know that this thing simulates solid body rotation. So the question is how roughly speaking can an array of vortices simulate solid body rotation? So I'm just going to sort of show you in cartoon form because we're not going to really do a precise calculation for this. So here, so this is going to be the cross section of the bucket. This is the axis of rotation. Like so, and then I'm going to draw in here a bunch of quantum vortex lines. So I don't know, something like this. And I'm going to, this picture's not going to be very good. So that's 1, 2, 3, 4, 5. Oh, drat. Okay, well, this should really be 6, but okay, there's 5 in this case. So what I want you to look at is let's look at two of these vortex lines. So let's choose those 2, for example. So let's expand that over here. So what will we see? So what we'll see then is one vortex line over here, another vortex line over here, and if I draw the superflow around them, something like this. And then this one, let's use a different color. And something like that. So let's suppose that this one, they're all going round in the same direction. So the flow is going like this. And then for the blue one, it's doing the same thing. Like that. And so what you can kind of see from this picture is that if I look at this region over here, you can see that in this region over here, the velocity is less here, cancels out. somewhat. And so what's going to happen then is that if I draw then the velocity as I go round here, I'm going to see as I go round the outside something kind of looking with big arrows like so, and as I go further in, these arrows get smaller and smaller. And so that's the basic idea for how this thing can simulate solid body rotation. So that's fine. So now the next question we should ask then is how much vorticity does each vortex line carry? And so the way we're going to answer that is we're going to answer this by computing the energy of the vortex line. And when I say how much vorticity, by vorticity I mean the circulation. And so this question is essentially the same thing as asking what is the value of n? So that's what we want to know. So what we're going to do now is we're going to compute the energy, and then of course we're going to ask, well, what is the value of n that actually minimizes the energy given the rotation rate of the bucket. So let's suppose that we have a vortex line. Let's draw over here. Let's suppose the height of this fluid is L, like so. So then the energy of a vortex of length L is just going to be the following. It's going to be the integral over space of a half rho s, the density of superfluid, velocity squared, that's the kinetic energy, d3r, like so. So that's what our energy is. And what it's going to be is the following. We're going to just substitute in our formula for the for Vs of r. This is the one that we worked out over here in the yellow box. And so what that's going to give us, if you write it out, E is equal to 1/2 rho s, the height of the fluid, L, the velocity squared, so that's n h over n squared, and then the integral of 2 pi r dr, because now this d3r wait, oh, that's why I'm confused. Let's try again. So that's why we get 2 pi r dr. And then what do we have? The velocity goes like 1 over 2 pi r. And so I'm going to get 2 pi r squared, because I've got the velocity squared in the kinetic energy, like so. And so now if you go and look at that, you can see, well, wait a minute, this I need to put some limits on this integral. So what are the limits going to be? Well, clearly the outer limit is going to be the radius of the bucket. So that we've called r. So this is the radius of the bucket r, and then what is going to be the lower limit? Well, we know that the vortex has a core size, which I'm going to now call r0, and so this limit has to we don't have any superfluid once we're inside the core of the vortex, and so the lower limit has to be R0, and so R0 is the vortex core size. Okay, so that's our energy, and now of course the 2 pi's and r's cancel, so we get integral dr over r, so we get a logarithm, and so now when we put it all together, what we get then is that E is equal to 1/2 rho s times L times NH over n squared times 1 over 2 pi, and then the logarithm of r over R0. And so what that tells you then is that the energy of the vortex line is proportional to n squared. Okay, so that's interesting. All right, so now we know that, but now the question is, well, we want to minimize the energy, but we also have to remember that we're keeping the vortex rotating at a fixed rate. What we want to do is we want to minimize the energy of the system subject to the constraint that we know what is the net what is the net rotation speed and vorticity. So think about it like this. I know how fast the fluid has to rotate. And so the question I have to ask myself is, do I have one big vortex just sitting in the middle and making the whole fluid go around? Or do I have lots of small vortices which together simulate the solid body rotation? So before I answer the question, so we can say it another way around, we can say, i.e., do we have one big vortex in the middle with a large value of n, or a lot of small vortices? Well, that's really a bad way of saying it. Let's say, or a lot of vortices with small values of n. So that's one way to ask, another way to ask the question. So what we have to say is we have a fixed rotation rate, and so if I have each vortex has vorticity NH over m like that, and how many, and what is the overall so how much vorticity do I have? So each vortex has vorticity of this, and then if I have n over little n vortices, that gives me NH over m as the overall vorticity. So what I do is I take the overall vorticity and partition it in amongst n vortices, and that's all I'm doing like that. So let's see what that means then. And so if I have that situation, then the angular velocity is going to be n over n, which is how many vortices I have, times the vorticity that each one has. So that's NH over M, and that's what I wrote down before, NH over M. And I have that the total energy is equal to N over little n, that's how many vortices I have, times this number here. Let's call this factor C1 times C1 times n squared. And so you can see that if you tell me what capital N is, a fixed capital N, i.e. total vorticity, total angular momentum, the energy is minimized with n equals 1. So the answer to our question then is very simple. If I have a superfluid that is rotating, it preferentially will organize into a whole bunch of vortices with the lowest possible quantum of circulation, rather than one big vortex. So the answer is over here. The actual answer that we see, that we just calculated, is that this is the possibility that we actually get. Lots of vortices with n equals 1. Absolute value of n is equal to 1. Okay, so that seems to answer that question, but we're not done yet with that. So the next thing that we need to talk about is what a page I have missing. Oh, well, never mind. Why do I have a page missing? Who knows?
So, Nigel?
Yes. Wait 1 second. I just wanted to check something here. Well, I don't care about the missing page, because I'm going to just carry on with what I want to say. So let me just write down what the next thing is, and I'll take your question. So this picture is fine. So this picture is fine. This calculation that we've done is fine, but we neglected interactions. Right? All we did was we assumed, we just added up the energy of individual vortices. And so obviously that's not quite right. And so the next thing that I want to talk about is the interactions between the vortices. Okay, so somebody had a quick question.
Yeah, I just wanted to make sure I was understanding the previous argument correctly. So if we were to recover the situation where we just had one big vortex, then we would have found that little n is just big N, right? Or am I not understanding that correctly?
Yes, that's correct.
Okay.
Yep. So we've got n amounts of vorticity.
Yeah.
That have to be partitioned between either n vortices, capital N vortices, or one vortex, or something in between.
Right. Okay.
Okay. So I'm going to talk about a few things. Some of the things I'm going to talk about are on the homework, the next homework that I'll release. And so I'm going to only give you a part of the calculations. So the goal in this section is to remedy this. So let's go straight on into it. And the first thing I want to compute is the angular momentum of a vortex at the center of a bucket. And in the homework, you're going to compute the angular momentum of a vortex that's not at the center of the bucket. So let's just so the picture that we're going to have is just the usual thing. So here is our bucket. Somewhere in the middle here, we have a quantum vortex line. The radius here is r. The height is L. Everything is rotating with some speed, capital omega like this. And the z direction is the one that is pointing up like so. And so what is the angular momentum in the z direction? So we can just simply write that down. So that's the integral from 0 to r 2 pi r dr of the integral from 0 to L dz of the angular momentum, which is the superfluid density times r times the superfluid velocity. And if you go and work that out, what you all see, just the integrals are easy. There's no divergences or anything like that. So you're just going to get rho s over m times pi h bar n times r squared times L. So that tells you that the angular momentum of a quantum vortex line is quantized, as you probably would have guessed. And and you can then extend this argument to a vortex that's off center. Okay, so I'm going to let you do that in the next homework. Now I want to talk about the interaction energy between vortices. So how do we work out the interaction energy? Well, what we do is we simply write down two vortices. So here's a vortex at R1 and a vortex at R2. And then, of course, we have the flow fields that go around these vortices. Sort of drawing like that. So something like so. We're going to assume that these vortices are parallel and are near the center of the bucket. And we're going to assume that this one has strength N1, this one has strength N2, and their velocity fields are V1 of R and V2 of R, like so. So let's suppose that I sit at some point in the superfluid. Then the velocity there is just the sum, V1 of R plus V2 of R, like so. And the energy of the system is just 1/2 OS times the integral V1 plus V2 squared d3R, like so. And we can expand that. So that's going to be the energy of vortex 1, the energy from vortex 2, and then there's going to be an interaction energy, which I'll call E interaction. And this E interaction is just the integral d3R of rho s times V1 of R dotted with V2 of R, like so. And so what we're going to assume is that the vortices are near the center. So we're going to assume that R1 and R2 are much less than the radius of the bucket. We're going to, without any loss of generality, put vortex 1 at the origin. And so that means that V1 of R is going to be H bar N1 over M R times the vector in the theta direction. And then the interaction energy is then just going to be rho S times L, the integral from 0 to R of R dr times H bar N1 over MR times the integral from 0 to 2 pi d theta of theta dot V2 of R. And so in these coordinates here, this is the radial vector, and this is the director in the angular direction. So anyway, in the tangential direction, unit vector. So anyway, so you can do a calculation, and that's what you're going to be asked to do in the next homework. Okay, so now I'm going to tell you the result of the calculation, and we're going to use this to see what happens to the stability of the vortex when we include these interactions. So homework 2 does the calculation. So I'm going to just tell you what the result is going to be. So what we're going to look at in the next section is the instability of vortices. With n greater than 1. So the same idea as we had previously, but now taking into account the interactions. So our goal in this section is to show that with interactions, a vortex of charge, topological charge, or strength n greater than 1 is unstable towards the formation of vortices with n equals 1. So that's what we're going to do, and let's start off then with a formula for the energy per unit length of our system. And so this is now essentially the answer to the homework exercise. So let me just write it down. So this in this formula here, the distance between our vortices is given by this d. So that's the distance between the center. And that d, of course, must be greater than the vortex core size. So we can use that inequality to compute what we need here. So since d is greater than R0, then this formula for E over L is going to be less than what would happen if I substituted for d, if I substituted R0. So the idea is then to substitute, replace d by R0 and get an inequality. And so if I replace this d by r naught, then I've got this factor of log of r over r naught, and I have another factor over here. And so I could write this as pi rho s h bar squared over m squared times n1 plus n2 all squared times the logarithm of r over r naught. That's because I've got n1 squared plus n2 squared over here and 2n1 n2 over here, but they're multiplied by different logarithms. But if I make the d and r naught be the same, then of course the logarithms are the same, and so I can write it down like this. And so the actual energy is less than this amount. And then what actually is this energy? Well, this energy is just the energy of a vortex line, of a single vortex, of strength n1 plus n2. So what that says is, what is the interpretation of that? So the implication is that the system can lower its energy if it has a vortex of strength n1 plus n2, a single vortex. So if it has a single vortex of strength n1 plus n2, it can lower its energy by making two vortices of strength n1 and n2 respectively. And with the total length being L. And so then now you can therefore iterate this process. And what that means is that every vortex will sort of fragment, if you will, into vortices of strength n is equal to 1. And so now you can see then that we're always pretty much doomed to only see vortices with n equals 1. Okay, so that's where I'm going to end for today's lecture. So next week we will talk about how vortices get nucleated, and we'll talk about how the superfluid state eventually dies away as you go to higher and higher rotations. So that's the end of today's lecture. So let me turn off